A sample of krypton is analysed in a time-of-flight mass spectrometer. The sample is ionised by electron impact to form 1+ ions. Give the symbol, including the mass number of the ion. So it's going to have a 1+ charge that reaches the detector first. So that's going to be the one with the lowest mass, or the lowest MZ, which is going to be this one. So the mass number 82, krypton, and it has a 1+ charge. Part B, calculate the relative atomic mass of krypton in this sample, giving your answer to 1 decimal place. So good exam technique here is just give yourself a little reminder that that's got to be to 1 decimal place. I need to calculate this abundance here. So that's going to be, now they're all percentages, so it's 100 minus 13.95, 2.33, 18.6, and that equals 65.12. So there'll be a mark for that. Second mark is for using the formula to write out the relative atomic mass. So 82 times 13.95 plus 83 times 2.33 plus 84 times the one we've worked out, 65.12, plus 86 times 18.6, all divided by 100, because the total abundance is in percentages, and percentages are 100. So there'll be a mark for the working out. That equals 84.0697. And it has to be to 1 decimal place, so that will be 84.1. And there's the third mark. C, give 2 reasons why it's necessary to ionise the isotopes of krypton before they can be analysed in a time of flight mass spectrometer. So they need to be ions so that they can be accelerated. And when they reach the detector, remember they pick up an electron, and if they're not ions, they won't be able to pick up an electron. So they can be detected. D, explain how ions are detected and the relative abundance is measured. So the way they are detected then, so they gain an electron, which generates a current. And then obviously the more of them there are, the more electrons are drawn, which means there is a greater current. So size of the current is proportional to its abundance. And then E, I know it says A there, but it's really E. In a time-of-flight mass spectrometer, ions are accelerated to the same kinetic energy, and we've got the formula there. Kinetic energy is in joules, mass needs to be in kilograms, velocity is in meters per second. In a time-of-flight mass spectrometer, each 84 krypton is accelerated with that amount of kinetic energy, and the time of flight is that, and we need to calculate the distance. So we know that velocity is distance over time, so distance is going to be velocity times time. I'm given time, but I'm not given velocity, but I can work out the velocity in here. But of course this mass here needs to come from the 84, but that 84 grams is of a mole, so I need to work out the mass of 1 ion in kilograms. So the mass of 1 ion in kilograms is 84, so divide that by 1,000 to get it into kilograms, and then divide by Avogadro's number, which gives me 1.395 times 10 to the minus 25 in kilograms, and there'll be a mark for that. We need to work out the velocity from that, so I need to rearrange the equation. So velocity is equal to 2 times the kinetic energy divided by the mass. So there's a mark for the rearrangement. Put the values in. So 2 times 4.83 times 10 to the minus 16 divided by 1.395 times 10 to the minus 25, which equals 83218. And then the last part, to work out the distance. The distance is velocity times time. Velocity is 83218 times time, which is 1.72 times 10 to the minus 5, which equals 1.43 meters.